Ultimately, in this unit of study, we want to answer the question, what happens when electricity comes from a generator? In other words, when we have a source of AC instead of DC, and we take that electricity and use it to drive a circuit that has a combination of inductance, resistance, and capacitance, right? Some amount of henries, some amount of ohms, and some amount of farads. Before we get all the way to the LRC series circuit, let's just consider what would happen if we took a generator and connected it strictly to a resistor. So the difference between this circuit and a resistor that's connected to a battery, a source of DC, is that the current does not flow in one particular direction. For a moment, the current flows clockwise, and then it comes back and flows counterclockwise and continues to oscillate back and forth. So if we make a graph of the current that flows versus time, we can say in general that the EMF of the generator is omega NBA cosine omega t plus phi, where phi represents some phase shift or phase relationship or phase angle. Well, let's just choose a frame of reference and let the phase angle be equal to 0. Now, knowing Ohm's law says EMF is current times resistance, then whatever is true of the current is true of the EMF. After all, the resistance would just act as some sort of a scaling factor. So if the graph for the driving signal from the generator is a graph of cosine, EMF versus time, omega NBA and negative omega NBA are the bounds. Well, if we were to divide by R, then we would have a maximum current equal to omega NBA divided by R. So let's just label I maximum and I minimum. And since the generator is inputting a signal that goes as a graph of cosine, then the current through the resistor goes as a graph of cosine. Okay, well, if you ask the question, what's the average current? It's pretty easy to come up with the answer. The average current is 0. There's just as much area underneath the curve when the current is positive as there is area underneath the curve when the current goes negative. So on average, there's 0 current. But that doesn't really answer the question, because I believe when we say what's the average current, we mean what's the average magnitude, discounting the difference between positive and negative. So one way we can answer that question has to do with a rectified circuit. Rectified circuits can be made in a few different ways. The easiest way to rectify the circuit, which really just means to get the current to only flow in one direction, to change AC into DC. So a diode can do the trick. A diode uses semiconducting material to allow current to only flow in one direction. Well, to state it briefly, diodes are made of silicon or germanium that are doped with impurities, and you can have p-type or n-type semiconductors. And a diode is made by butting a p-type and an n-type up against each other. So we have what we call a PN junction. Here's my p-type, here's my n-type. Now p-type just means the semiconductor has been doped with a little bit of positive charge carriers. So we know in circuits that conduct electricity using copper wire, that the charge carrier are the free electrons of the copper. And we've made the distinction between drift velocity and current. So if these electrons in the copper wire drift to the left, then we say conventional current flows to the right. In a p-type semiconductor, the charge carriers are these positive impurities. And so if current flows to the right, that's because these positive charges are flowing to the right. In an n-type semiconductor, you guessed it, the impurities are negatively charged particles. And so for the current to continue to flow to the right, the negatives would have to drift to the left. So what would happen if we connected this PN diode to this sort of polarity? What if we connected this end to negative and this end to positive? Well, then these little positive charges in the p-type would want to drift to the left, and the negative charges in the n-type would want to drift to the right. And what would happen is this the gap in between the two would turn into something called a depletion zone, and nothing would conduct across that gap. Of course, nothing conducts across that gap to begin with. There is actually a little bit of a gap between the two types of conducting material. However, if this is p-type and this is n-type, and you reverse the polarity and make this side positive and this side negative, now the positive charge carriers drift in toward this gap, and the negatives drift in toward the gap, and they fill in the gap and negate each other, and the current can flow to the right. So in other words, a p-n junction like this will not allow any current to flow to the left, but it will allow current to flow to the right. So a better symbol for a diode like this looks something like that. So if we take our generator and pass the electric current through a diode, so now our resistor, generator, and diode are all in a series loop, then the output voltage, the resulting current through the resistor wouldn't quite look the same as it does without the diode present. What happens is, instead of a graph of current versus time that looks like this, the diode gets rid of those parts of the graph. No current can flow in the reverse direction. So the diode allows the current to flow clockwise during the moments in time when the EMF from the generator is positive. But once the EMF of the generator goes negative and the current would come back counterclockwise, the diode blocks that current. So this would be a rectified circuit, and we can ask the question, what's the average current? But still, we're going to have to average some positive values in with some zero values that exist for moments in time. So what we'd have is a pulsating behavior of whatever this resistor happens to represent. If it's a light bulb, it would flicker a little bit. If it was a speaker, the sound would be slightly intermittent. Of course, that would depend on exactly what is the frequency of the generator. So there's another way to rectify, and it looks something like this. This one's called a bridge rectifier. The bridge rectifier circuit doesn't just get rid of these negative portions of the graph, but actually has a way of turning the negatives into positives. Let me show you how. So again, here's our generator. And instead of just one diode, we're going to use a system of 4 diodes. And we'll hook them up something like this. Okay, hopefully you're with me so far. So what happens in the moment in time that the generator is trying to drive a clockwise circuit? Then the current, let's see, comes around, gets to a junction, and then this diode wouldn't allow the current to go that way, but it would allow the current to go this way. But then it gets here, and this diode would block it. So here's what we're going to do. We're going to connect our resistor across these points A and B. So when the generator has a positive EMF and drives the current clockwise, the current gets to point A, can flow across the resistor, makes it to point B. This diode lets it continue on this way and complete the current loop. So which way is current flowing through the resistor? To the right. Now let's go half a cycle later to the moment in time that the generator now has a negative EMF and tries to drive current in a counterclockwise direction. So the current continues and gets to this junction. This diode blocks it, so the current can follow through this diode and it gets to A. That diode would block it, so the current goes to the right through our resistor, makes it to point B, is passed by this diode, and it completes the loop. So this rectifier circuit allows the current to be AC, and it can cycle back and forth clockwise and counterclockwise, but whenever it reaches the resistor, it only flows in one direction through the resistor. So if we were to graph the current through the resistor, it's always positive, meaning it's always flowing to the right. So now the question is, what's the average value? Well, this gets a little bit tricky, but we can call this the RAV, the rectified average value. And it would go something like this. Find the area underneath the curve. I guess this represents half a cycle, and this represents a full cycle. So let's find the area underneath the curve for a full cycle, and then divide it by this amount of time to get some sort of effective time average. In other words, what constant value could have been maintained for that same length of time to produce the same amount of average. Okay, so that's the idea of how we could express an average value for this rectified circuit. There's another way to express an average value. You don't actually have to rectify the circuit. We don't need to use diodes in a bridge rectifier. Let's go back to our original design and just say we have a generator connected to a resistor, and that's it. So as you know, the problem with this, because the EMF itself is cycling sinusoidally, then the current through the resistor is changing sinusoidally, and the average of that is 0. However, we can make a graph of current squared versus time. Well, negative values squared become positive, and so this gives us a graph that would look like this. All the negatives turn into positives by virtue of squaring the values. And then in the same way, we could take the area underneath this curve for one full cycle, and then ask the question, what steady value could have been maintained for that amount of time, and produce the same total area. Of course, in the end, we're going to have to take the square root of that, because whatever this value is, let's just call it, well, let's call it I squared average. So we have to take the square root of the average value squared in order to get the average value. And so this is referred to as the RMS value. It's not RAV for rectified average value, it's RMS for the root mean square value, meaning the square root of the average or mean value to this graph. So in our next video lesson, we'll go through mathematically how we can calculate RAV values and RMS values for electric current in a circuit where the electricity through a resistor is provided by a generator.